Hi everyone. Today we are continuing our study of the periodic table by looking at group 7A, the halogens. So we've got a few learning objectives. We're going to be learning the properties of the halogens and the properties of nonmetals in general because halogens are not metals. We're going to be adding to our periodic table, and by doing so we're going to be shading in the halogens, and we're also going to figure out the charge of all of the ions in column 7A. Before we get started, make sure you're all set up. You are going to need your periodic table. You are going to need colored pencils. And you're going to need pencil and paper for taking notes. I really recommend taking notes on this lesson, and in particular, I recommend taking notes on paper. There are going to be a few drawings that I ask you to add in, and it's really hard to do that in a Google Doc. So first off, let's talk about the nonmetals. This might surprise you, but nonmetals are things that are not metals. The nonmetals on the periodic table tend to be on the right-hand side. There is one exception, which is hydrogen, element number 1. They tend to have lower melting and boiling points, which means you don't have to get them that hot to turn them into a liquid or a gas. That's why things like oxygen or hydrogen are gases at room temperature, while things like sodium and magnesium are solids at room temperature. They form anions, negatively charged ions, with the exception, once again, of hydrogen. Hydrogen forms an ion with a charge of +1. And most importantly, the nonmetals are capable of a special type of bond called covalent bonding, which means sharing valence electrons. This kind of bond lets them make really big, complicated molecules, much more complex than you can get with ionic bonding. So once we learn about covalent bonding, we're going to be coming back to these nonmetals, and they'll be really important. So we are talking about group 7A. I want you to take a moment, pull out your periodic table and a colored pencil of your choice, and I want you to shade in these 6 elements. It's column 7A, so not the very last one, but the second to last column. And I want you to color in fluorine, chlorine, bromine, iodine, astatine, and tennessine. Make sure you add a key at the bottom of the periodic table. Label it nonmetals, and then underneath that have your halogens and whatever color you decided to make that. Go ahead and pause now while you color that in, and then unpause when you are ready. All right, you ready? Before we move on, I want you to take a moment and look at that list of elements. Which of them look familiar to you? Have you heard of fluorine or fluoride being in anything that you use? Have you heard of chlorine anywhere? Have you ever used iodine or bromine? Think about those elements and where you've heard them. And we'll talk about what these things are used for next. So the important thing to understand about the halogens is that they are toxic. They're extremely toxic. These things are poison, and the fact that they are poison is what makes them useful. If you've heard of fluorine, you might know that fluorine is something that they will turn into, they'll use for dental treatments. So if you live in a rural area, you might get fluoride dental treatments regularly, like I did when I was a kid. If you live in a city, they've probably already added fluoride to your drinking water because it helps kill bacteria and strengthen your teeth. So fluoride in your water can prevent tooth decay. It's not enough to do anything bad to a creature of our size, but for bacteria it can be very bad. Likewise, we stick chlorine in our swimming pools in order to clean them, because what chlorine does is it can kill bacteria. Enough chlorine can kill anything, but as with all poisons, the dose makes it. So the amount of chlorine that is really dangerous to bacteria that might live in our swimming pools actually is safe for us. If you have ever gotten blood drawn at a doctor's office, they might have had a wipe with a sort of weird reddish-brown liquid. That's bromine. And they might wipe down an area before you give blood in order to make sure that they don't put any bacteria from your skin inside your body with that needle. So it's really common to wipe down areas with bromine. It's a medical disinfectant. Again, it kills things. It's toxic. And the fact that it kills things is what makes it useful to us. If you've been using Clorox wipes in order to clean your areas, those are probably made either out of chlorine bleach or out of alcohol, which, though it's not a halogen, does share a little bit of a property with them. And then if you've ever gone backpacking or hiking and had to sanitize your own drinking water, one common technique for doing so involves adding a few drops of iodine into your water and letting that sit for about half an hour to kill any bacteria or protists or viruses that might be living in that water. So all of the halogens are incredible disinfectants. It's one of their most important and most useful properties. So before we go any further, I want you to take out your notes and I want you to draw a planetary model, really a Bohr-Rutherford model with the electrons in the quadrants all neatly, of both fluorine and chlorine. So fluorine and chlorine. Fluorine is element number 9. Chlorine is element number 17. I want you to draw them in your notes, and once you've drawn them, take a moment and ask yourself, what do these things have in common? What is similar about those two ions, or those two atoms, and what charge ion would they make? So remember, when you're forming an ion, atoms are trying to either gain or lose electrons to fill that outermost electron shell. So think about how many electrons they would need to gain or lose, and figure out what charge ion you're going to have. Go ahead and pause the video now and hit resume as soon as you've finished drawing those two atoms in your notes. Ready? All right, so your drawing should look a little bit like this. Your unpaired electron could be in any quadrant, but the important thing to note is that you should have 2 electrons in that first quadrant, and you should have 7 electrons in that second shell. So 2 electrons in the first shell, 7 in the second shell. And for chlorine, we've got 2 in the first shell, 8 in the second shell, and again, 7 valence electrons in that outermost shell. So the thing about the halogens is every halogen, because it's in group 7A, is going to have 7 valence electrons. And because they have 7 valence electrons, in order to become ions, what they will do is they'll gain 1 extra electron. And when they gain that 1 extra electron, they will become ions. And that 1 extra electron is going to give them all a charge of -1. So all halogens form ions with a charge of -1. So above your halogens on your periodic table, I want you to go ahead and fill in -1 up here. So you can see that over here. The important thing to remember about this is because they can form an ion with a charge of -1, they're going to want to bond with any cations that can form a charge of +1. So in particular, these things really love to bond with the alkali metals, and they really love to bond with hydrogen as well. Now halogens we already mentioned the fact that halogens can react with alkali metals to form salts. In fact, the name halogen means like the generator of salt. In fact, any chemical compound where you have a metal as the cation and a halogen as the anion is going to be a type of salt. So that's another way that you can identify a salt as a specific class of chemical compound. So some examples of salts, you could have lithium fluoride, 1 lithium, 1 fluorine. You could have sodium chloride, table salt. You could have magnesium bromide, but there you would need 2 bromines to balance out the 2 positive charges from the magnesium. Or you could have aluminum fluoride, which has 3 fluorines to balance out the 3 positive charges from the aluminum. Now, the other thing that I said that the halogens were really good at reacting with was hydrogen. In fact, whenever you have a hydrogen as your cation and a halogen as your anion, you can form a strong acid. So remember, acids and bases are sort of opposites of each other. We learned about bases when we talked about the alkali metals, and we said that if you had an alkali metal and a hydroxide anion, you could form a strong base. Here, if you have a hydrogen cation and a halogen anion, you will get a strong acid. And remember, one of the ways that we can detect acids is through the use of chemicals called indicators, which basically will change colors depending on the presence of acids or bases in a solution. So some examples of strong acids, you could have hydrofluoric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, or hydroastatic acid. All of those are strong acids formed with a hydrogen cation and a halogen anion. So when we talk about acids and bases, remember that what we're really doing is we're thinking about water as an ionic compound. And in that ionic compound, there is a cation, a single hydrogen cation, and there's an anion, a hydroxide anion. Remember, hydroxide, OH negative, is a polyatomic anion, which means a negatively charged ion made of more than one atom, in this case, oxygen and hydrogen. You can think of those two things, the hydrogen cation and the hydroxide anion, as pieces of a water molecule. Now, if you have neutral water that is not acidic or basic, if it's just plain water, you have the same number of hydroxides as you have hydrogens. However, if you have extra hydroxides, then you have a base. And if you have extra hydrogen cations, then you have an acid. So the reason why something like hydrochloric acid, HCl, is an acid is because if I pour that into water, I'll be adding more hydrogen cations, so it becomes more acidic. And we're going to talk about acids and bases more soon. All right, so let's talk about reactivity. With halogens, the smaller the atom is, the more reactive it is. And there's a reason for that. Remember, these things are trying to gain electrons to form ions. So if they're trying to grab an extra electron, you want the space for that electron to go to be close to the nucleus. Remember, atoms are like tiny magnets. The nucleus is positively charged. The electrons are negatively charged. Electrons are drawn towards the nucleus. Now, if your spot that you can fit an electron is really close to the nucleus, like with fluorine, it's got an open spot in the second shell, then that's really reactive. But if the spot where you can fit an extra electron is many shells away, then that becomes much harder to grab that extra electron. So something like astatine or tennessine is not nearly as reactive as something like fluorine. In fact, fluoride is the most reactive anion on the periodic table. It's extremely reactive. All right, hopefully that was a good primer on the halogens. Keep up the great work, folks.